Hello my friends, today we're going to be talking about how to solve some enthalpy problems. I'm going to show you two problems. One called the calculating molar enthalpy. So we're going to learn how to take some data from a lab and turn it into molar enthalpy. And then also we're going to calculate the heat of reaction when we know the molar enthalpy. How can we figure out how much heat's given off then? Let's get started. So consider this reaction here. This aluminum chloride solution, so it's aqueous, it's a solution, reacts with a sodium hydroxide solution, and it produces a precipitate of aluminum hydroxide and dissolved sodium chloride. Now when we ran this in the lab, what happened is we took 50 mils of a 0.4 molar solution of aluminum chloride, mixed in with that 50 mils of a 1.5 molar solution of sodium hydroxide, and then we just measured the temperature change of those two solutions when they're mixed together. So as I look at this problem, I notice a few things. First thing that jumps out at me is I'm given a starting amount of my aluminum chloride of 50 milliliters, but also the starting amount of my sodium hydroxide. So the first thing that comes to mind is says, ooh, wait a second, I need to do a limiting reactant problem here because I don't know which of these is going to run out first. But I did also notice when I said it, I was like, oh wait, this is 0.5 and this is 1.5. So my sodium hydroxide solution is 3 times stronger than my aluminum chloride solution, but the same volume. That means there's 3 times as many moles of sodium hydroxide as there are of aluminum chloride in the solution. And if you notice, I need 3 moles of sodium hydroxide for every 1 aluminum chloride. So that tells me right away that these two are going to run out perfectly together. They're going to be balanced out nicely. They're both the limiting reactant. So as I move forward, I can use either the 50 milliliters of the 0.5 solution or the 50 milliliters of the 1.5 molar solution. All those numbers are valid numbers to use because they're both limiting reactants. All right. But in this problem, I'm looking for the delta, the molar delta H here. So the molar change in enthalpy for aluminum chloride, not the sodium hydroxide. So that's kind of making me think that maybe I'm going to be using this aluminum chloride numbers more than I will be the sodium hydroxide numbers. All right, so let's get rolling. So if I know I'm going to need to find the delta H, I know that the delta H of the reaction is just equal to the heat given off or absorbed by the reaction. So the delta H is equal to Q. So I need to find the Q of the reaction. Now I can't necessarily do that right away. I can find, though, the heat absorbed by the water and then back out the heat of the reaction from that. It should just be equal but opposite in sign. So let's do that. So this is the heat gained by water. Awesome. And to do that, I normally use this Q equation. So Q is equal to the mass times the specific heat times the change in temperature. So the heat absorbed. And then I'm just going to plug in some numbers here. So Q is equal to the mass, which in this case, we have 50 milliliters of solution, 50 mils of solution. That's going to equal 100.0 grams of solution. Now, this works because in our solution, these solutions will actually weigh more than 50 grams, but they're going to have approximately 50 grams of water in them because the volume the aluminum chloride takes up is really small. So it dissolves in nicely and fits in between the molecules, and it doesn't add to the volume very much. So that's why we can use that 1 gram per mil density of water, even though these densities might be significantly off. So the next thing we do is find C, and we're going to assume again here that this dissolved solid in the solution doesn't have a huge impact on C, so we're going to assume it's still 4.18 joules per gram degree Celsius. It's really not this number, but it should be pretty close. If you wanted to, you could just measure that in your solution. You could do some experiments and measure what the exact value is in your solution. We won't till we'll assume it's the same. And then the delta T is going to be this 26.3 degrees Celsius, minus 22.5 degrees Celsius. And in the end, we get a Q value of this problem of 1,588.4 joules. And I'll wait here to round until I get to the end of the problem. I know I'm going to round to 3 sig figs at the end. All right, so that's my Q value, and that's my heat of reaction. So that's how much heat Ooh, that's not true. That's the heat the water absorbed. I apologize. The heat of the reaction, Q, is equal to negative 1588.4 joules. Because if the water absorbed this much heat, then the reaction gave off this much heat. This is the heat of reaction, and we like to call that delta H. All right, so our delta H is negative 1588.4 joules. And that's great for this particular reaction with this volume of solution, and these two molarities. That's how much heat you would get. But we want something a little more universal. We want to be able to tell everybody how much heat you would get per mole. So to do that, all we do is we take our delta H here and we divide it by the number of moles. So we say that negative 1588.4 joules divided by, now we've got to figure out the number of moles we have. I should have done that already. Let's do that over here. So this is the number of moles. And here we want in terms of aluminum chloride. So we're going to focus on how many moles of aluminum chloride we had. If we wanted to find out for the sodium hydroxide, we'd focus on how many moles of sodium hydroxide we had. But here, so let's find out. So number of moles, that's going to be of, AlCl3. That's going to be N is equal to the molarity times the volume. N is equal to the molarity of 0.500 molar times the volume of 0.0500 liters. So N is equal to 0.0250 moles. And I add that extra 0 because there are 3 sig figs everywhere. So I want to keep 3 sig figs right there. And this is, of course, moles of aluminum chloride. Now I'm going to take this number of moles and put it in right up here in the division. So 0.0250 moles. And here this is my molar delta H. When I divide these two, I get a delta H value equal to negative 63,500 joules per mole of aluminum chloride. So my delta H can also be written as negative 63.5 kilojoules per mole to get rid of that big number there. And this is the value that we might then put into a textbook or onto a table to let people know how aluminum chloride works in this reaction. So for every 1 mole of aluminum chloride, you'll get 63,500 joules of energy. Now we didn't get that much in our reaction, but that's only because we only had a very small number of moles. We didn't have a full mole. All right, so far so good. Let's do one more. So in this problem, we're going to take a look at ethane burning. And it burns an oxygen in the reaction here. So we have, 1 mole of C2H6 ethane needs 7.5 moles of oxygens, 2 moles of carbon dioxide, and 3 moles of water. And don't sweat this 7.5 thing because these are moles. You can easily have half a mole. So basically this is 3.5 moles of O2 or 7.5 moles there. And we know the delta H of combustion, and this is kilojoules per mole of ethane. So it's quoted in terms of ethane. So every time this happens, you get this many kilojoules out of the reaction. So the question now is, how many joules of heat will be given off when there's 56.5 joules of ethane is burned, or sorry, 56.5 grams of ethane is burned. So we know that we get this many kilojoules per mole. The only question now is, how many moles is 56.5 grams? So to figure that out, we come down here and we say, okay, this is number of moles of C2H2. And to do that, we just take the mass of C2H2, which is 56.5 grams. We divide it by the molar mass of 30.07 grams per mole. And we end up with 1.88 moles of C2H2. So if we know that 1 mole gives off this much, 1.88 moles is going to give off 1.88 times that. So our delta H, so this is the heat given off by 56.5 grams. So delta H for this reaction of 56.5 grams is going to equal negative 1561 kilojoules per mole times 1.88 moles. Moles cancel here, leaving just kilojoules, and we end up here with an answer of 2,900. So my delta H is 2,933 kilojoules. Now, technically the problem asks for joules, so we want to multiply this by 1,000 and quote our delta H as 2,933,000 joules of energy are given off. Awesome. Now 1 joule of energy is actually a pretty small amount of energy. That's why it's such a large number here. So 1 joule, if you imagine the energy it takes to take about an apple, about 1 Newton, and lift it up 1 meter over your head, that's about a joule of energy. And you don't get very tired from that, so a joule is pretty small. All right, my friends, those are the two types I wanted to show you. Best of luck to you.